open loop transfer function. The steady state characteristics of DC drives are of major importance in the selection of a DC drive and are not sufficient when the drive is closed loop controlled. Knowledge of dynamic behavior, which is normally expressed in the form of a transfer function, is also more important. The circuit arrangement of a converter fed separately excited DC motor as shown in the figure. The motor speed is adjusted by setting a reference voltage VR, assuming a linear power converter of the gain K2. The armature voltage VA is given by K2 VR. Let this be equation 1. Now, assuming that the motor field current IF and the back EMF constant KV remains constant during any transient disturbances, the system equations are EG equals to KV IF omega, equation number 2, VA equals to RM IA plus LM dIA by dt plus EG. Now you can substitute the value of EG here. Then you are going to get RM IA plus LM dIA by dt plus KV IF omega. Let these two equations be 3. And torque developed TD is given by KT IF IA. Let this be equation number 4. And TD in mechanical terms is given by J d omega by dt plus B omega plus TL, which is equals to KT IF IA. Let this be equation number 5. The transient behavior may be analyzed by changing the system equations into Laplace transformations with zero initial conditions. Then these equations will transform into Laplace equations that VA of S equals to K2 VR of S. Sixth equation, EG of S equals to KV IF omega of S. Let it be 7. Then this equation will become VA of S equals to RM IA of S plus LM S IA of S plus KV IF omega of S. Let this be equation number 8. In terms of EG also we can write this, that VA of S equals to RM IA of S plus SL IA of S plus EG of S. TD of S equals to KT IF IA of S. TD of S equals to KT IF IA of S, which equals to S J omega of S plus B omega of S plus TL of S. That is equation number. This is 9 and this is 10. Now we'll try to write these equations in output by input form. Then the equation number 6 we can write this, VA of S divided by VR of S equals to K2. And 7 we can write EG of S divided by omega of S equals to KV IF. The 8th equation, VA of S minus, I'm taking this term this side, then EG of S divided by IA of S equals to RM plus SL. And we can write this equation as, this is actually the input, this is output, so IA of S divided by VA of S minus EG of S equals to 1 by RM plus LM. Now the equation number 9 we can write as TD of S divided by IA of S equals to KT IF. Equation number 10 we can write this as omega S. Omega S divided by TD of S minus TL of S equals to Sj plus B. From the equation number 8 we can write the armature current IA of S equals to VA of S minus KV IF omega of S divided by S LM plus RM, which again we can write this as VA of S minus KV if omega of s divided by, we'll take out the Rm, then we'll be getting s tau a plus 1, where tau a is the Lm by Rm, which is time constant of armature circuit. From equation 10, omega of s equals to Td of s minus Tl of s divided by Sj plus B. That equals to Td of s minus Tl of s divided by, we'll take the B term common, than s tau m plus 1, where tau m equals to J by B, which is nothing but mechanical time constant. Now, from the output by input form, number 6, if we represent this in block diagram, this is output and this is input, K2 is the system, then VA of S, VR of S. From this equation, we can relate VA of S minus, this is KV I of omega S, which is nothing but EG. We can add up here, this is plus and this is EG of S, which is a negative value from this equation. IA of S is the output, VA of S minus EG is the input for this system. 1 by taking the Rm outside, S tau A plus 1. Output will be IA. From this equation, that this Td of S is the output, I of S is the input, and this is the system. So I of S, Kt, IF, then the output will be Td of S, this one. Td is the input minus Tl of S. So this is Td plus and minus Tl, which is given to 1 by B S tau m plus 1. Then the output will be omega of S. Equation that Eg and omega S are related with Kv If. So Kv If, this is open loop block diagram of separately excited DC motor. Equation that is be 11 and this be 12th equation. The 12th equation gives us the speed and 11th equation gives us the armature current. Now, from this diagram, we can see that we have two possible disturbances, that is VR of S1 and here TL is the another disturbance. So, the steady state response can be determined by combining the individual responses due to VR and TL. As VR and TL both are the two possible disturbances. Now, we will nullify the one disturbance, that is TL equals to 0. So, response due to a step change in the reference voltage VR is obtained by keeping TL equals to 0 in block diagram. Then omega S divided by VR of S is given by K2 KV IF divided by Rm B divided by S square tau A tau m plus S tau A plus tau m plus 1 plus KV IF whole square divided by Rm B. And this can be found by using the formula when the feedback system is there in control system. This is G of S and this is H of S, negative and positive, cos and C of S, R of S, then R of S divided by C of S is given by G of S divided by 1 plus H of S and G of S. By using this formula, we can find this. The response due to change in TL can be obtained by keeping VR equals to 0 in the black diagram. Omega S is the output divided by TL of S is the input, then 1 by B is tau A plus 1 divided by S square tau A tau M plus S into tau A plus tau M plus 1 plus KV IF square divided by Rm into B. Let this be equation number 13 and this be 14. The block diagram. This is the open loop block diagram for torque disturbance input. From this block diagram, we got this equation. Now, using the final value theorem, the steady state relationship of a change in delta omega due to the step change in control voltage V of S and the step change in the load delta TL can be found from the equations number 13 and 14 by substituting S equals to 0. Then equation number 13 will become change in omega equals to K2 kV IF divided by RMB plus kV IF whole square change in VR. That is equation number 15. Then equation number 14 will become change in speed omega equals to minus Rm divided by RMB plus kV IF square delta TL. That is equation number 16. So this is regarding separately excited DC motor steady state analysis. We have seen the steady state characteristics of a separately excited DC motor. Now we'll see the DC series motor. The DC series motors are used extensively in traction applications where the steady state speed is determined by the friction and the gradient force. By adjusting the armature voltage, the motor may be operated at a constant torque or current up to the base speed, which correspond to the maximum armature voltage a chopper fed or controlled DC series motor drive is as shown here. The armature voltage is related to the control or the reference voltage VR by a linear gain constant K2. Assuming that the back EMF constant Kv does not change with the armature current and remains constant, the system equations are Va is equals to K2 VR, let this be equation 17, Eg equals to Kv Ia omega, 18th equation, Va equals to Rm Ia plus Lm d Ia by dt plus Eg, that is equation number 19, Td equals to Kt Ia square, that is equation number 20, and Td in mechanical terms is given by J d omega by dt plus b omega plus TL, that is equation number 21. The equation number 20 contains a product of variable type non-linearities, and as a result the application of transfer function technique would no longer be valid. However, these equations can be linearized by considering a small portions at the operating point. Let us define the system parameters around the operating points, that is Eg equals to capital E G naught plus delta E, Ia equals to Ia naught plus delta Ia, Va equals to Va naught plus delta Va, Td equals to Td naught plus delta Td, omega equals to omega naught plus delta omega, Vr equals to Vr naught plus delta Vr, TL equals to TL naught plus delta TL. Recognizing that delta Ia, delta omega and delta Ia square are very small, then tending to a 0, then equation number 17 to 21 can be linearized as delta Va equals to K2 delta Vr, delta Eg equals to Kv Ia naught delta omega plus omega naught delta Ia, delta Va equals to Rm delta Ia plus Lm d delta Ia by dt plus delta Eg, delta Td equals to 2 kV Ia naught delta Ia. Similarly, delta Td is given by J d of delta omega divided by dt plus b delta omega plus delta TL. transforming these equations into Laplace domain, which is going to give us delta VA of S equals to K2 delta VR of S. Let it be equation 22. Delta EG of S equals to KV IA naught delta omega S plus omega naught delta IA of S. Let it be 23. Delta VA of S equals to Rm delta IA of S plus SLM delta IA of S plus EG of S. Let this be question number 24. Then delta TD of S equals to 2 kV IA naught delta IA of S. Let this be 25. Delta TD of S is equals to Sj delta omega S plus B delta omega S plus delta TL of S. Let this be equation number 26. These 5 equations are sufficient to establish the block diagram of a DC series motor. Let us draw the block diagram as we drawn in case of a separately excited DC motor. This is open loop block diagram of chopper fed DC series drive. From this block diagram, it is evident that any change in either reference voltage or load torque will result in a change of speed. And here we can see the block diagram when the reference voltage is changed by keeping the load torque equals to 0. And this one is the block diagram for the change in the load torque when the reference voltage is 0.